Okay, we still have two problems left to cover in section 4.6 on proofs involving Cartesian products of sets. So this number 69 says let A, B, C, and D be sets. Then A cross B union C cross D is a subset of A union C cross B union D. Before we get into a proof, let's think about what each of these sets looks like. So remember, the Cartesian product of two sets consists of ordered pairs. The Cartesian product of C and D will consist of ordered pairs. So you have a set of ordered pairs and a set of ordered pairs, and you're unioning them together, so it's just a bunch of ordered pairs. Now what do we have on the right-hand side? A and C are just sets, so A union C is a set. B and D are set, so B union D is a set. You have a Cartesian product of two sets, so the right-hand side, that set consists of ordered pairs. So we have a set of ordered pairs contained in a set of ordered pairs. So both sides involve ordered pairs. Now, how do we show one set is a subset of another set? Right? Remember, you can say, for the left-hand side to be a subset of right-hand side, the if-then statement is if something is an element over on the left-hand side, then it is also an element of the right-hand side. So basically, we're proving an if-then statement directly. So what do? Assume we have something on the left-hand side. Now remember, elements of this set on the left-hand side are ordered pairs. So we're going to say let x, y be an element of the left-hand side. Okay? Don't try to do 8 things in one step. So you start with an element on the left-hand side. Now, how did I know to start with x, y? Because I argued before elements on the left are ordered pairs, so I picked an arbitrary ordered pair. Let's just go with our gut. What does it mean for x, y to be in this union? Then that means x, y is in A cross B, or x, y is an element of C cross D. Okay, that's just definition of union. Again, if you feel like the reader needs to hear that, you could say, by the definition of union, we get x, y is in A cross B, or x, y is in C cross D. And now, what do you think we're going to do next? We have x, y as an element of A cross B, or x, y as an element of C cross D. We have an or statement. We don't know which one applies, so we have to go into cases. Again, you can label your cases case 1, x, y is in A cross B, or case 2, x, y is in C cross D. I just stated the cases. I don't feel like I need to write case 1, case 2. Again, the key word that tells my reader I'm going into cases is the word if. If you want to start a new paragraph to indicate you're shifting gears, that's fine too. So if x, y is an A, B, I'm telling the reader I'm going into the first case. Well, what does it mean for x, y to be an element of A cross B? The definition of Cartesian product says x is in A and y is in B. Right, so that's about as much as I can do just going with my gut here. I mean, what else are you going to do, right? You have x is in A and y is in B. There's nothing to destruct anymore. Let's stop and think about what I'm trying to get to. I'm trying to get this ordered pair xy is in the right-hand side. Okay? Well, what does it mean for xy to be in this Cartesian product? I need x in A union C. I need y in B union D. Well, we just said x is in A. So x is going to be in A union C. We just said y is in B, which means y is in B union D, right? If y is in B, it's going to be in the union. If x is in A, x is going to be in this union. So let's just say that. So x is an element of A union C, and y is an element of B union D, right? We just said x is in A, so x will be in the union of A, anything else. Y is in B, so y will be in the union of B and anything else. So I have x is in this set, I have y is in this set, so the conclusion is xy is an element of A union C cross B union D. Now, I'm not going to state at this point that we have subset, because that was just our first case, right? So we have to do the other case. It's very similar. It's so short, I mean, you could argue without a loss of generality, but it's basically the same. I'll just write it again. Now, what if the other case was xy was in C cross D? Then what does that mean? That means x is in C and y is in D, right? X is in C and y is in D. So, same argument as before. If x is in C, X is in the union of A and union C. And if Y is in D, Y is in the union B union D. Right, so hence, I'm using the same verbiage as I did before to tell the reader it's the exact same argument. Hence, where is XY? Right, X is in A union C, so XY is in A union C. Cross Y is in B union D. So notice we started with an XY on the left-hand side. In each case, we got XY was on the right-hand side. So what's the conclusion? Therefore, we get A cross B union C cross D is a subset of the right-hand side. Oops. And there's our proof. Now you don't have to show containment both ways because it just says subset, right? Remember, if you're trying to show two sets are equal, you do containment both ways. It's only said one way, so we don't try to do the other way. Okay, so that's our first proof, that number 69. The next one also involves a Cartesian product, two Cartesian products. Okay, so it says, suppose we have A, B, and C are non-empty sets. Okay, notice that this previous problem didn't specify non-empty. And if I put a note to myself here, for this example, you really only need C as non-empty in this proof. So we'll have to see where that comes into play. Okay, so it says A, B, and C are non-empty sets. And it says then A cross C is a subset of B cross C if and only if A is a subset of B. Okay, that's what we're trying to prove. Okay, so we need to think about our logic here like we did in this problem the other day. So we have an if and only if proof. Remember, if and only if means if this condition is true, then this condition is true. And also, if this condition is true, then this condition is true. Okay? Now the good news is, unlike the one we did in class the other day, there's no equal to. So there's no containment both ways. So we have to assume if this is true, then this is true. And then if this is true, this is true. Okay. Let's just for fun, let's start with this. Okay, let's start with this. Okay, so I'm going this direction. Okay, so again, assume. Well, here, let me just put the let. So I'm going to go ahead and restate the hypothesis here. Let A, B, C be non-empty. Okay, so that's the general assumption. I'm going to start with this condition. So assume A is a subset of B. Okay. That's all we have. There's nothing to work with here. There's nothing obvious to do next. Now, what are we trying to show? I'm trying to show that A cross C is contained in B cross C. So the Cartesian product, this is a set of ordered pairs, is contained in this set of ordered pairs. Now, how do you show one set is a subset of another? We start with an element in here, show the element is in here. So let's pick something in A cross C. So I'll just use X's and Y's again. Let X, Y be an element of A cross C. Okay, so I don't try to do 8 things in one step. So I started with something on the left-hand side. Well, what does this mean? That means X is in A and Y is in C. X is in A and Y is in C. That's the definition of Cartesian product. Now let's think about what we're trying to get to. I'm trying to get XY. I started with XY and A cross C. I'm trying to get XY is in B cross C. So what do we need? We need X is in B and Y is in C. Well, we already have Y is in C, so the only thing left to show is that X is in B. Now, why is X in B? Well, we said X was in A. A is a subset of B. Anything in A will also be in B. So that's what we need. So even though I just said, I think I'll write the reason. Since A is a subset of B, well, let me write them both. Since X is in A and A is a subset of B, we conclude that X is in B. So I stated several facts here. There's 1, 2, 3, 4 facts. So I'm telling the reader the two I'm using here. So since x is in A and A is a subset of B, we conclude that x is in B. Okay, so now we have x is in A, we have x is in B, and y is in C. Right? Thus, that tells me xy is in B cross C. So I started with an xy and A cross C. I got xy and B cross C, so A cross C is a subset of B cross C. Hence, A cross C is a subset of B cross C. Okay, so we're halfway through. So that was assume A is a subset of B, show that A cross C is a subset of B cross C. I'm not sure where we use the empty set here, the non-empty. Okay, so let's go the other way. I'm probably going to have to erase. Okay, so now let's assume this. Okay, so now let's assume A cross C is a subset of B cross C. Okay, and now we want to show that A is a subset of B. That's what we're trying to show. Okay, right, so we're assuming this. We want to show A is a subset of B. So what do? How do we show something? We pick something in A and we show that element is in B. So let me pick an element in A. Let X be in A. Okay, so X is in A. Now, yeah, here's the kicker. We're trying to get that X is in B, right? We picked X in A, we're trying to show X is in B. We need to use this fact about Cartesian products here, that A cross C is a subset of B cross C. But what's the problem? I don't have an ordered pair. If I have an ordered pair in here, because I assume subset, that ordered pair would also be in here. But I don't have an ordered pair in here. I just have a single element in A, right? You see the difference here is, right, we assumed we had an ordered pair in A cross C, and then we used the fact about A is a subset of B on one of the coordinates. Now we're starting with an A, something in here. We don't have an ordered pair to say is contained in the other one. So we have to create an ordered pair. That's where the C non-empty is coming into play. Okay? So we didn't really need A and B non-empty here. So I need to create an element in this set, so then we can say the element's in this set. Okay, so since C is not the empty set, there exists, I'll just call it Y. Little c would make sense, but there exists a Y in C. Since C is non-empty, I know there's an element in the set. So what do we have here? I have an element X in A. I have an element Y in C. So that means XY is an element of A cross C. So do you see, I had an element in A. I'm trying to create an element in A cross C. But I don't have an element in C, but since C is non-zero, there is one, so I just called it Y. Okay, so now XY is an A cross C, and now we can use our hypothesis. A cross C is a subset of B cross C, so I already said since. Let's say it follows that XY is an element of B cross C, since A cross C is contained in B cross C. Again, I'm telling you, we mentioned a long time ago. I went ahead and mentioned it again, right? So XY is an A cross C. It's in here. Because this is a subset of B cross C, that means XY is also in B cross C. Okay? So now, did we accomplish what we wanted to accomplish? I was trying to show, I assumed this is true. And I'm trying to show A is a subset of B. Okay. So now I picked an X in A, I still have to get an X in B. Notice I had to stop and see where I was, right? I'm trying to show A is a subset of B. I picked an X in A. I need to show X is in B. And here we are, right? We have XY is in B cross C. That means X is in B, doesn't it? Thus, X is an element of B. So I started with X is in A, I got X is in B, that gives me A is a subset of B. Right? I picked an X in A, I got X was in B, so that means A is a subset of B. So that's both directions, right? I started with assume this, show this, assume this, show this, and so we're done. So I should probably write a little conclusion. Therefore, I'm just going to restate the whole thing. A cross C is a subset of B cross C if and only if A is a subset of B. So there's our proof for both directions. Okay, so those are the last two examples in that section.